Hello once again, class, and welcome to another mock lecture. Not a lot of introduction here. Today we're going to be going over graphing transformations for sine and cosine, so let's just jump right into it. First thing we need to discuss is a sinusoidal graph in general. Both sine and cosine are wave-like functions, and anything that imitates a wave function is called sinusoidal. So sinusoidal functions are what we're going to be transforming today, really just of a specific form. But you can transform other functions in a similar manner. Some key characteristics regarding sinusoidal functions: they all have an amplitude, which is the height of your wave, above the line of equilibrium, which is the line that the sine function or cosine function oscillates around. In this case, it's the x-axis, but it's just the height of the wave. And then there's a wavelength or a period. Oftentimes we refer to it as lambda. That's the variable that we give wavelength. But that's it, right? Those are the only two key characteristics of sine functions or cosine functions or sinusoidal graphs in general. A lot of things can be modeled with sinusoidal waves. Here's a few, right? Electricity, tides, weather, sound waves there's a really big application there. But then if you want to be less scientific, you can also look at horoscopy type things such as biorhythms, right? Those are also sinusoidal based on your birthday. So these are the things we're going to be transforming. Anything that looks like this. We want to look at how does A, B, C, and D, right, these four different transformation variables, how do they change the sinusoidal wave? So I want to look at Desmos, play around with these variables a little bit, and then we'll come back and quantify exactly what these things are doing. All right, so here I am on Desmos, and honestly, this is just where I go. This is like my sandbox for learning how things change graphs. Especially in a transformation sense, like what would happen if we changed A? What would happen if we changed B or C or D? So I set up some sliders, right, for all those things, and I'm just going to move these around so that we can see how are these things affecting the graph. So I've got the sine graph here. That's the thing that we're going to transform. And I think I want to start off with the shifting stuff before we get into the dilations. So D, if I just move the slider for D, and keep in mind that what's happening here is basically, and I guess I should point this out, and this is basically as it is right now, where all these things are just 1, 1, 0, and 0. This is actually just the function sine of x. So A is 1, B is 1, C is 0, D is 0. What would happen if we changed D? So this would become like sine x plus something or sine x minus something. And the plus or minus is happening on the outside of the parentheses. All that's happening is it's shifting up or down, depending on what D is, right? And it's shifting in a way that you would expect. So plus D plus 5.4 moves the graph up 5.4. Minus 2.9 moves the graph down 2.9. Okay, so that's all D does. It controls the vertical positioning of the sinusoidal curve. C, okay, C is a shifting. Now you might expect if D moves it up or down, C is going to move it left or right, especially since it's definitely affecting X first and foremost. That makes sense. And you'd be right, okay? If I move the slider to the right, the graph moves to the right. If I move it to the left, the graph moves to the left. However, the thing to mention here is that if I make C 2, for example, the function itself will actually say x minus 2, and yet it's a shifting to the right that's occurring. Okay, so I'm going to put C back to 0 here and try and really explain this by looking at this function, okay, which is sine of x minus pi over 3, which is a movement to the right of pi over 3. So let's talk about why is this moving the graph to the right when it looks like you really should be shifting it left. It's got the negative in front of it. The reason why is pick a value. I think 0 is a really good value. Normally, right, let's say we're just looking on the interval negative pi over 2 to pi over 2 here. Normally, the value that gives you 0 on the sine graph would be 0 inside that interval. But we're delaying when that's happening now by a pi over 3. Right? So now to get 0 in the sine function, you actually have to plug in pi over 3, which is right here. That will give you 0 in the sine function, which would, of course, output a 0 as the y-coordinate. So by subtracting stuff away from x, you're delaying when it happens. So things happen at a later, I'm using kind of time as my analogy here. So maybe we can pretend the x-axis is time. We're delaying when 0 occurs on the x-axis, right? When the y value of 0 occurs on the x-axis. And that's why an x minus appears to shift things to the right, whereas an x plus would actually shift things to the left, because now you're advancing values. Now negative pi over 3 gives you 0, which is going to output 0 for y. So that's why things shift in that specific way. Okay, now let's talk about a and b. Now a controls the amplitude. If a, and essentially all you're doing is you're multiplying the y values by whatever a is. So a is really the amplitude, right? It's the height of the wave above the x-axis, or it's the height above the wave above its line of equilibrium. When a is bigger than 1, you're just multiplying, and actually even when it's less than 1, you're just multiplying the amplitude by whatever that specific value is, right? So like 3.4 gives you an amplitude of 3.4. This height now is at 3.4, at the very top. Okay, that's how that works. And really what you're doing is you're multiplying the distance away from the x-axis that all of your points are, which is why the points that are on the x-axis are still on the x-axis. So like, for example, at pi over 2, we're normally 1 unit away from the x-axis, but if I use 3 sine of x, I'm multiplying that distance by 3, so now at pi over 2, the y-coordinate is now 3 units away from the x-axis. But things that are on the x-axis, right, if you're 0 units away from the x-axis, like at pi, multiplying that distance by 3 is still 0 units away. So that's why the amplitude kind of stays. It doesn't change x-coordinates or x-intercepts. It just changes the height of your wave. If it's smaller than 1, then it's like compressing the graph a little bit. And if it's negative, the graph flips over the x-axis. So if your a is -1, the amplitude's still 1. Amplitude's always going to be the absolute value of whatever a is. But now the wave is inverted. Right, so at pi over 2, instead of being at 1, now we're at -1. And then, of course, I can change the amplitude. Let's say we want to make it -3, and then I want to change this to be 3 sine of x, right? It's the same wave, it's just been flipped, and that's all the negative sign does there. Okay, so let me put this back to 1. And, of course, 0 just makes everything 0. So you get y is equal to 0, and that's not really a sinusoidal curve anymore. So it's got to be non-zero for a. B compresses or stretches your wave horizontally. So it's a horizontal dilation. So as I increase, and this is again interesting, as you increase B, you're actually pressing the wave closer together. And as you decrease B, still being greater than 0, it's actually stretching it out. So this is a wave, and what we're doing is we're changing the period, you might notice. So if B is 1/2, the period is actually 4 pi. Right before it starts repeating again. So we start at -2 pi, and then we go all the way to 2 pi before it starts repeating the same pattern. That's a period of 4. Whereas if I make B 2, now a period is just pi. Start at 0, now we're repeating ourselves at pi. So the period formula, right, to find wavelength, very closely tied to what B is. And of course, if B is negative, then it flips over the x-axis. Over the y-axis. So now we've flipped it horizontally instead of vertically here, right, is what we're doing. And of course we can flip it and compress it, but that is what B controls. All right, so let's get back to the main presentation here and consolidate all this information onto one place. Okay, so let's write down some of the things that we discovered. First, a, the absolute value of a, determines the amplitude of the wave. If a is less than 0, then the sine wave or the cosine wave gets reflected over the x-axis. B determines the wavelength, specifically the absolute value of B. If B is greater than 1, the wave is compressed, whereas if it's between 0 and 1, then the wave gets stretched out. A little bit of a counterintuitive behavior, with what's happening there. If B is less than 0, then the wave gets reflected over the y-axis. Now there's also a formula, right, that we need to talk about in regards to B. B isn't the wavelength or the period itself, it helps determine it. Period is actually looking at what a normal period for sine is, which is 2 pi, and then breaking it up into B pieces. Sometimes that means making it bigger if B is between 0 and 1, and sometimes that means making it smaller Like, for example, if b is 4, you can find the period by breaking, what we mean is 4 periods now have to fit into 2 pi, as opposed to 2 pi being the period. We're breaking it up into 4 different cycles now. So the period overall would be 2 pi divided by 4, or pi over 2. So this is a formula that we're going to need to know in today's video. C and D take care of the shifting. C shifts the graph horizontally. It's oftentimes referred to as the phase shift. And then one of the things that we saw was that things are moving counterintuitively. So x minus c actually shifts the graph to the right because you're delaying when specific y values would happen, whereas x plus c advances things. So things happen before their time. So that shifts the graph to the left. And then finally, D is the vertical shift. It does what you'd think it would, shifts it up or down. If it's addition, it's up. If it's subtraction, it's down. The key thing to remember here is that it does not change the amplitude. It just shifts the line of equilibrium. And that's it. Now, just as there's an order of operations, there is an order of transformations, so the order matters here. Luckily, the order is pretty much what you'd expect it to be. Take care of the things inside the parentheses first. So that's C. So your first thing you're going to do is shift the graph left or right. Then you're going to move on to figuring out what the period is, right, or what the wavelength is. Then you're going to figure out what the amplitude is, and then you're going to shift the graph. So the first and last things that you do are shifting. First thing you do is shift left or right. Last thing you do is shift up or down. It doesn't really matter the order that you do these things in, but this is the order that I'll go with for the video. First horizontal shift, then we're going to determine wavelength, then we're going to determine amplitude, then we're going to do shifting vertically. Okay, so let's get into some examples. All right, so the first thing I want to do is just look at some key features based on equations that were given. So we're not graphing anything in these two, we're just figuring out what is the amplitude and what is the period. First thing we'll take care of is the amplitude, because that is typically the easiest thing. You basically just look at what A is. So the height of the wave above the line of equilibrium in both cases is going to be 2 and 10 respectively. And that's just because we're looking at the absolute value of the A value, which in this case is positive 2 and positive 10 respectively. The next thing we're going to do is we're going to figure out what is the period. So you can take B and you can just do some division, right? 2 pi divided by whatever B is going to give us the period. For the top equation, that means that 2 pi over 3 is the period. For the bottom equation, it means that 4 pi is the period, because 2 pi divided by 1/2 is the same as 2 pi times 2 over 1, and that's 4 pi. Some other key features, we can look at how it's being shifted, and this question doesn't ask us to do this, but I just thought I'd throw it in since we're looking at this stuff anyway. The top equation's shifted up 3 because D is 3. The bottom one's down 1 because D is -1. It's the phase shift that's weird here. Also I should mention B is reflected over the x-axis since we do have a negative sign here. But the phase shift, for this one, is easy to see that the phase shift is left, pi over 2. This one, not so much. Typically, things are supposed to be written as B and then x minus c, but that's not really how the inside of this sine function is written. So to get it in that form, you'd have to factor out a 3, which would make the inside x minus pi over 3. So it appears that pi over 3 is the phase shift, and it's to the right. Now, as far as graphing goes, there's two main approaches. For some reason, I don't know why, because typically I do like to do things visually, but I prefer to do things with a table. And that's the method I'm going to start with. But if I go through this and you're like, Mock, this is awful, I don't want to do this. Well, just hang tight, because we're going to go through the visual approach as well. Okay, so first, let's talk about the parent tables of sine and cosine. Parent tables are always the table that you're going to start with, and the tables method, right? To be super clear, you're just manipulating tables. That's all you're doing. And then you get an ending table, and that's the thing that you're going to graph, basically, at the end. Now, sine and cosine start at different places. When you start at 0, which is what I'm going to do, of the parent table, I just basically included basically the unit circle, quadrants 1 through 4. So it's one period that we're looking at. And I highlighted him here in this. By the way, I was in a very pastel mood. That's why I use a lot of kind of pastel colors, except for this kind of neon blue and neon red thing. But other than that, I don't know why I'm talking about this. Let's continue with the lesson. What was I saying? Oh, right. So I put one period on the theta column here, And then I'm just going to list out these really easy to graph y values at these specific points. So for cosine, the pattern is 1, 0, negative 1, 0, 1. For sine, it's 0, 1, 0, negative 1, 0. And those are the tables that we're going to start with when we start manipulating them to do the transformations. So let's say that I want to graph y is equal to 1/2 cosine times 2x minus pi over 2 minus 1. First, we're going to start with the parent table here. Now, going by the order of transformations, the first thing we need to look at is the phase shift. But again, we see that this inside, the phase shift is not right pi over 2. I guess that's the first thing to kind of point out. You want to make it look like the b times x minus c sort of deal. Boy, that looks terrible, but that's the normal standard form of things that we want things to look like when we do transformations. So I'm going to factor out a 2, right? And doing so gives me 1/2 cosine times 2, or of 2, times x minus pi over 4. Now you might be wondering, how did you get pi over 4? Well, just look, if you distribute the 2 back in there, that'll get you back to here, right? And that's what you want to have. And then the minus 1 is still on the outside. By the way, mock from the future here. I just realized that I used x in the problem, but I'm using theta in my tables. I don't think I made that mistake later on, but just to kind of point that out, these really should all say cosine x and x. Let's get back to the lesson though. Okay, so then now that we've got the phase shift out of the way, we see that it's pi over 4 to the right. We're going to add pi over 4, and so what I did is I just added pi over 4 to all these things. 0 plus pi over 4, pi over 4. Pi over 2 plus pi over 4, 3 pi over 4. Right, so on and so forth down the line here. The period is still 2 pi because 9 pi minus 4, or 9 pi over 4 minus pi over 4 is still a distance of 2 pi. Now you might be wondering, why did you add? Why did you add pi over 4 when it clearly says minus? Well, remember, things are always opposite. It's opposite land inside the parentheses here. We're actually moving the graph to the right. We're delaying things. We're delaying y values from happening by pi over 4, and that's why I had to add in this case. So next, we're going to take care of wavelength. Now this is the most annoying one to take care of, regardless of whether you're going tabularly, I don't know if that's a word, or the visual approach. But we need to first figure out what is the period. So I'm going to take 2 pi, divide it by 2, and we're going to find the period is pi. So when I move on to the next table, and I'm going to, here by the way, I didn't really describe this, but like I like to draw an arrow that says a transformation is happening. I write something that tells me what transformation it is. In this case, it's wavelength. And then I put something that's going to help me know what to do to that specific column. Phase shift and wavelength affect the x column, whereas vertical shift and amplitude affect the y column, which is why I'm just copying down the y column for these, because they're not changing, right? Nothing's happening to y. This is all just affecting x. So anyway, the period is pi, which means that when we start our new x column, our new theta column, then we will have pi over 4, but we don't want to end at 9 pi over 4, right? That would be a period of 2 pi. We want this amount of oscillation, right? We want this specific oscillation to happen in pi amount of space instead of 2 pi. So then I'm just going to add pi to pi over 4, and I should end at 5 pi over 4. Now the question is, well, then what are these values here? Well, luckily, the way that we've broken up the parent table, it's really in 4 distinct sections. 1, 2, 3, 4 main pieces. So let's just take the period and divide that by 4 to figure out what I should be adding at each step in order to finally end at 5 pi over 4, because 4 additions need to take place for me to get to here. So if I add pi over 4, 4 times, so pi over 4 plus pi over 4, that's pi over 2, plus pi over 4 again is 3 pi over 4, and then plus pi over 4 again is pi, and then finally the 4th addition of pi over 4 would give us 5 pi over 4. So this is correct, right? This is the way to do this. By the way, I just wanted to point out, if 2 ended up being negative or happened to be negative, you just put a negative sign in front of all these things. Just multiply that column by negative and you're fine. Okay, moving on now to the amplitude, and this one's pretty easy to take care of. You're just going to multiply all of your y values by whatever the number is, right? So again, at this point, maybe not again, but at this point, the x column is set in stone. Don't have to do anything to it. It's done. So it's going to be pi over 4, pi over 2, 3 pi over 4, pi, and 5 pi over 4. The y column is going to change though. We're going to multiply all these values by 1/2, and that's going to give us this. If a were to be negative, then I'd just multiply them all by negative 1/2, and I would get this table. It's not negative though, so we'll go back to this. Okay, that's it. That's amplitude. The vertical shift, similarly easy, in my opinion. You're just going to subtract 1 from all of these things now. 1/2 minus 1 is -1/2, 0 minus 1 is -1, so on and so forth. And then we're finally done. We just need to graph this thing. So then I go to the graph. I put on here the dotted line, that's normal sine graph, normal cosine graph. But now I'm just plotting this table. So pi over 4, -1/2, that's this thing. Pi over 2, -1, here it is. 3 pi over 4, -3/2, right? Here we go, right? And then just kind of going along. Remember to, when you're graphing these things, to make them curved, right? Sine and cosine aren't like a Charlie Brown shirt, right? They're more curved, so you need to make sure that you put that curve in there. And that's it. Then I just extend that, and that is the graph of 1/2 cosine of 2x minus pi over 2 minus 1. Maybe I should double check if this is correct. Okay. Here's another one, and I invite you to pause the video, give this one a shot. Yeah, it's a little bit of work. Graphing transformations by hand do take a little bit of time, but I think once you get the hang of it, it's actually not too bad. Okay, so first thing that I would do is I would figure out what is the period, since, and this one's interesting because pi over 2 is b. You're going to take 2 pi, divide it by pi over 2. It turns out the period is just the number 4. Doesn't involve pi in it at all. So when I did my graph here, right, here's all the transformations that are happening. Notice that I was a little bit lazy when I did the phase shift. I just wrote it as 1 plus pi over 2, 1 plus pi, 1 plus 3 pi over 2, 1 plus 2 pi, because none of this stuff ends up mattering, right? Once we reorganize the period to now just be a distance of 4 units, then I just start at 1 and end at 5. And that's a really nice way to take care of the period. Amplitude, just multiplying all the y values by 3 gives me this stuff, and then adding 1.5 to all that gives me this. So here's my graph, and then I extended it in purple to the left and to the right. Now, there's a second method for doing this. So if we just went through all that stuff and you're like, Mark, this was awful. I don't want to do things with a table. I'm confused. I don't know what's going on. Maybe the visualized approach is for you. So first thing, and I guess the first thing to point out, is that with the visual approach, the order of transformations is kind of weird. You're allowed to do them in a different order just by the way that I'm going to show you how to do this stuff. So for me, like the first thing I do is I move the line of equilibrium, right? Which again is the line that your graph is oscillating around. So if I go back to the previous slide, I'm just basically shifting the whole cosine function up 1 here. Okay, so visualized approach, the first thing you're going to do is you're going to move the line of equilibrium. Second thing you're going to do is you're going to shift the starting point. So we're going to take care of the phase shift. All right, so now I'm going to move every single point, really just I'm going to call it the starting point. For cosine, right, it starts 1 unit above the line of equilibrium. For sine, it would actually start on the line of equilibrium. But since this is cosine, I'm just moving that back to the left pi, because that's what the phase shift is. Move left pi. Next, I'm going to account for any change in amplitude. The amplitude should be 2. So above the line of equilibrium, we need to go up 2 units. Okay, so that's a pretty quick one. And then we're going to have to figure out the period. So whether you're going with tabular stuff or visual stuff, you can't really escape having to figure out what the period is. Here, 2 pi over b becomes 2 pi over 4. So a period is very short. It's only pi over 2. So in this amount of space, a whole oscillation needs to take place. A whole period takes place in pi over 2 distance. Now, so I broke the period into, I kind of jumped a little bit here, but I broke the period into 4 equal pieces. So on the graph that I had, every 2 little tick marks I wrote, okay, well, here's the key features. And cosine and sine have a pattern based on their parent tables. Cosine's pattern is above the line of equilibrium by an amplitude's distance. then on the line of equilibrium, then below the line of equilibrium by an amplitude's distance, then on the line of equilibrium again, and then above the line of equilibrium by an amplitude's distance. Sines is on, up, on, down, on. But cosine, the one we're using, is up, on, down, on, up. Hopefully this makes sense and I'm not just like sounding like a crazy person by saying all this stuff. But maybe when I actually graph it, it'll make a little bit more sense. So again, that's why we put these little tick marks here. So what I'm going to do is I'm just going to go through this pattern. So my step is now to just draw this thing. So we're up, we're on, we're down, we're on, we're up, right? That's cosine's pattern. And the up and down is by an amplitude's distance. So I'm using 2 as the distance to go above and below, right, the line of equilibrium. And then I just extend this pattern. Up, on, down, on, on, down, on, up, right, so on and so forth until I've filled out the axes. So that's a lot of information. Hopefully it makes sense. If you need to go back and rewatch parts of the video, definitely do so. If you have questions or comments, please leave them in the comments section. Thanks a ton for watching, guys, and I'll see you in the next one.